In this video, we will do some very fundamental discussion on the concept of friction, right? Before we get into the details of friction. Let us begin with a very, very simple example. Let's say this is a road on which we have, say, a wheel, right? Or a ball, right? And let us say we apply a force F onto this ball. What we observe is that this ball will start rolling, right? And after some time, it will come to a halt, right? It will stop rolling, right? So it starts its journey from this particular point and ends the journey over here, right? When this force is applied, it starts moving this ball in this direction, but throughout its journey, there is an opposing force, right? Which is acting on this, which is reducing its velocity, which is de-accelerating the ball. And this force, which is reducing its velocity, is known as frictional force, F. All of you are aware of this, right? So a frictional force comes into play throughout its journey. It keeps on reducing the velocity, and finally the velocity over here becomes, the final velocity becomes zero over here. So this is frictional force is a force which is an opposing force, which in case of moving body reduces the velocity, right? Let us think about this slightly in more depth. Let us say we have a table surface. Let us say this is a table surface, and let us say there is a block of wood on this. Let's say this is a block of wood lying over here, and I'll assume that the weight of this is, say, for example, 12 Newton. Right? So it's lying over here. It is in equilibrium. Let us say I apply a force onto this particular block of wood, right? Force. And let us say I begin with a very, very small magnitude of force. Say, for example, the applied force is to begin with, say, for example, 1 Newton, right? A very small force. Our observation is when this small force is applied over here of 1 Newton, the block does not move. Now, you have applied a force and the block is still in equilibrium, it is not moving. That means there has to be an opposing force, which is nullifying this force, which is opposing this force and preventing this block from moving. And it turns out that this opposing force is the friction force between the block of the wood and the table. So if the applied force is, say, for example, 1 Newton, the frictional force which is applied by the block is also 1 Newton. So 1 Newton and 1 Newton, they are acting in opposite directions, as you can see over here, and the block remains in equilibrium. If I increase this force to, say, for example, 2 Newton, again what will happen is that we see the block does not move. That means the opposing force has become 2 Newton. If it would remain 1 Newton, then this force would be more than 1 Newton and the block would start moving. But since we are seeing that the block is not moving at all, even though we have increased the force to 2 Newton, that automatically means that the opposing force has also become 2 Newton. And this continues, right? As I keep on increasing this force gradually, the frictional force also keeps on increasing, right? Till a time, right, we reach, say, for example, 12 Newton, or maybe 12.1 Newton or anything. So when I apply a force of 12 Newton or maybe 12.1 Newton, slightly more than the weight, what would happen is I would see that this particular block of wood would start to move. It will not start moving on this stable surface, but I see that it starts to move, right? And the frictional force at that time is also 12 Newton probably. The moment I increase the force to, say, for example, 12.2 Newton, right, the block starts moving. The block starts moving on this surface and you see it's moving over here. When it starts moving over here, the frictional force is still 12 Newton. Right? It is not that the frictional force has become 12.2 Newton. If the friction force would become 12.2 Newton, these two forces would again cancel out each other and the block would remain stationary. Since we are seeing that the block has started moving, that means the force applied is larger than the frictional force. So this frictional force now remains constant at 12 Newton. And as I keep on increasing this, say, for example, I make it 14 Newton, the frictional force still remains 12 Newton. The additional 2 Newtons is being used to move this and accelerate the block of wood on the stable surface. This is how the applied force and the frictional force get related. If I try to show this in the form of a graph, I'll get a graph like this. If I have a graph of applied force versus frictional force, or rather let me take frictional force over here on the y-axis, frictional force over here, and let us the applied forces on the x-axis. So if I draw a graph of force, frictional force versus applied force, I'll create a graph something like this, right? Something like this. Okay. Let us try to analyze this graph. Let us call these points O, A, B, and let us say C. Right? Now, the part OA, if I look at the part OA, is the part where as I keep on increasing the applying force, the frictional force also keeps on increasing. So that is this particular part. Here, as I keep on increasing the applied force, the frictional force keeps on increasing. If it is 5 Newton over here, here also I will have 5 Newton. See? And this particular part, or this particular friction which is there, which keeps on increasing as the applied force it keeps on increasing, is known as static friction. Static because the block of wood is still not moving. So static friction. Finally, we reach point A, which is this particular point. Right? This particular point. So here, the static friction assumes its maximum value. Right? 12 Newton. That's the maximum value of the static friction. Right? And this particular point, or this particular frictional force, is known as limiting friction. Limiting friction. After reaching point B, we see the graph going slightly down. That means what happens is that this frictional force decreases slightly. Maybe this, instead of being 12 Newton, may become 11.9 Newton. The reason why that happens is the frictional force slightly decreases is because the object has started moving. And when an object is moving, the friction decreases slightly. So maybe instead of writing 12 Newton over here, I should write maybe 11.9 Newton and maybe 11.9 Newton. So there is a small reduction in this particular frictional force. The reason, as I said, is because the block is moving. Right? And then what we observe is that as the applied force keeps on increasing, as we keep on, the frictional force remains constant, 11.9 Newton. Right? So this is how frictional force changes with reference to applied force. Okay. As far as this part is concerned, when the block has started moving, part BC, right? So OA is static friction. Then point A represents limiting frictional force. Limiting friction force. So this is point A. So this friction, this particular value is the limiting friction force. We call it limiting friction because that's the maximum value of the static frictional force. Right? Over here, right? This is the maximum value. Therefore, we call it limiting friction. And part A, part BC, we call this kinetic friction. Kinetic friction because the object now has started moving. The frictional force has become constant. Right. So the frictional force acting on an object, which is on which a force is being applied, can be divided into three, or essentially two parts: static friction and kinetic friction. This is only the maximum value of static friction. So we have two types of frictional forces: static friction and kinetic friction. Here the object is stationary. Here the object is moving. Okay, I'll end this video over here. This is just a brief introduction to friction. As we go along, we will talk in detail about frictional forces and various other types of friction, for example, rolling friction, in future videos. Thank you.